In 1977, the American Institute of Architects handed out one of its most prestigious honors to a building that had spent the previous 5 years dropping £500 glass panels onto public sidewalks. The same building had been covered in plywood for so long that Bostonians had given it 2 nicknames. The Plywood Palace, the world's tallest plywood building. The same building had required 500 tons of emergency steel reinforcement because the engineers studying its wind response were not fully confident it could survive a severe coastal storm. And the insurance company, whose name was on the facade, one of the largest in the country, could not actually move their own employees inside. The American Institute of Architects gave it a National Honor Award anyway. That is not a footnote in the story of the John Hancock Tower. That is the story. To understand how a 60-story glass skyscraper in the middle of Boston became the most dangerous building in the city, you have to go back to the late 1960s, when the John Hancock Mutual Life Insurance Company decided it needed a new headquarters. Not just a functional one, a statement. The kind of building that announced, in glass and steel and sheer vertical mass, that this institution was permanent, confident, and modern, in a way that nothing around it quite was. Back Bay was the right location for that kind of ambition. It was already home to some of Boston's most architecturally significant buildings: brownstone rows, Victorian streetscapes, and directly adjacent to the site Hancock had selected, Trinity Church, HH. Richardson's Romanesque masterpiece from 1877, one of the most celebrated religious structures in American architecture and a designated National Historic Landmark. Hancock hired I.M. Pei and Partners, one of the most prestigious firms in the world. The design responsibility fell to Henry Cobb, a partner known for precise geometric minimalism. Cobb's concept was disciplined and striking in equal measure. A 60-story rhombus-shaped tower, narrow on 2 sides and broad on the other 2, sheathed entirely in reflective glass. No ornament, no setbacks, no visible structural expression. Just a sheer blue mirror rising over Copley Square. The reflective glass was not incidental. It was the architectural argument. The building would not compete with Trinity Church. It would mirror it. The brownstones, the church spires, the sky itself, all of it reflected back in blue glass, as if the tower were absorbing its surroundings rather than dominating them. On paper, it was a compelling idea. A modern building that acknowledged its context by disappearing into it. That idea did not survive contact with the ground. Boston's Back Bay is not naturally occurring land. In the mid-1800s, the city systematically filled in tidal mudflats, gravel, sand, and whatever fill material was available, to create buildable acreage out of marshland. The resulting soil behaves accordingly. It is soft, wet, and sensitive to lateral pressure in ways that punish any construction project that fails to account for it carefully. Engineers working in Back Bay have understood this for over a century. Some have understood it only after it was too late. In 1968, as crews excavated the foundation for the Hancock Tower, the temporary steel sheeting installed to hold back the surrounding soil warped inward. The soft clay and fill pressed against the retaining walls from outside, and the walls moved. That movement did not stop at the construction fence. It propagated outward through the neighborhood, displacing ground and destabilizing whatever sat on top of it. UT lines buckled, sidewalks cracked and dropped, and across Clarendon Street, Trinity Church, the building the tower had been designed to honor by reflection, began breaking apart. The mortar joints in the stonemasonry split. Stained glass windows dating to the 1870s shifted in their frames. Interior murals and decorative plasterwork sustained damage. A structure that had stood without incident for nearly a century of Boston winters and urban development was being physically undermined by the excavation happening next door. The tower meant to respect Trinity by mirroring it was not even above grade yet, and it had already begun destroying it. Trinity Church filed suit in 1975. A Suffolk Superior Court jury found in the church's favour and awarded approximately $4.17 million. With interest accumulated across years of litigation, total liability estimates exceeded $11 million. The Massachusetts Supreme Judicial Court upheld the verdict. One of the largest insurance companies in the country had been held publicly accountable in court by a 19th-century church it had cracked apart during construction. That outcome was significant. But it was, in retrospect, the opening act. The Hancock Tower's facade consisted of approximately 10,344 large insulated glass panels. Each panel measured roughly 4 feet by 11 feet. Each one weighed approximately 500 pounds. They were dual-pane insulated units with a reflective chromium coating applied to the inner surface of the outer pane, bonded to the building's metal frame with rigid solder. Together, they formed the seamless blue skin that gave the tower its defining visual character. While the building was still under construction, around 1972, those panels began to crack. In high winds, they did not simply crack. They separated from the facade entirely and fell. On January 20th, 1973, a winter storm moved through Boston with winds reaching approximately 75 miles per hour at the upper floors. Over the course of that single storm, at least 65 panels failed. Some fractured in place. Others detached from the building's skin and fell hundreds of feet toward the streets and sidewalks surrounding the tower. In the months that followed, more than 100 panels across the tower's early construction and initial operating period are reported to have failed, sending shattered glass or intact 500-pound sheets toward Copley Square. Boston police began establishing wind protocols. When gusts approached 45 miles per hour, surrounding streets and sidewalks were closed. An office tower in one of the city's most visible and prestigious neighborhoods had been reclassified, functionally, as a falling object hazard zone. Nobody could yet explain why. Early theories focused on the building's movement. Some engineers proposed that the tower swayed under wind load and that aerodynamic pressure concentrated at specific points along the facade, popping panels out of their frames. Others suggested the ongoing foundation settlement from the excavation damage was producing enough differential movement to stress the glass loose. The architects, the glass manufacturer, and the building's owner entered into non-disclosure agreements that suppressed technical findings from the public record and complicated the path to any straightforward answer. When the explanation finally emerged, it was less dramatic than the theories and more damning. The rigid solder bonding the chromium-coated dual-pane units to the metal frame could not accommodate the natural dimensional movement of the glass. Temperature cycling caused the panels to expand and contract. Wind vibration introduced repetitive microstresses across the surface. In a properly designed connection, those movements would be absorbed by a flexible bond. In the Hancock Tower, the rigid solder transferred every one of those stresses directly back into the glass itself. Fatigue cracks formed, propagated slowly, and then reached a threshold where the panel fractured, or separated from the facade entirely when wind conditions pushed it past the point of failure. The panels were not being blown off the building. They were being slowly destroyed by the system designed to hold them in place, and then released when enough damage had accumulated. While engineers worked through that diagnosis under the cover of non-disclosure, the building's exterior communicated the situation to everyone in Boston who had eyes. More than an acre of the tower's facade was covered with painted plywood panels, substituted in where the glass had been removed or had failed. Blue painted boards, visible from across the skyline, replaced the reflective chromium skin that had been the central design idea of the entire project. A building conceived as a seamless mirror had become a checkerboard of glass and plywood, stretching 60 stories above Copley Square. Esquire published a piece calling it Boston's Big Pain in the Glass. The Globe covered every new failure. Local radio hosts treated the building as a recurring punchline. Hancock executives were quoted expressing frustration that they had over $100 million committed to a building their own employees still could not occupy. That framing captures the specific quality of the situation, not just financial loss, but the particular indignity of a company built on the business of assessing risk, having produced the most visible, uncontrolled risk in Boston. The fix, when it finally came, was total. Every one of the 344 original insulated dual-pane panels was removed and replaced with monolithic heat-treated tempered glass, single-pane units that eliminated the fatigue-prone, laminated construction entirely. Contemporary estimates placed the cost of the reglazing between $5 and $7 million in early 1970s dollars. Time magazine reported that combined renovation costs, including the glass replacement and structural work, added roughly $15 million to the overall project, pushing the final tab past $150 million, approximately double the original $75 million estimate. The replacement glass solved the falling panel problem. It introduced a different one. The original insulated dual-pane units had provided thermal separations in between the building's interior and the exterior climate. The single-pane tempered replacements did not. Boston winters are long. Boston summers require cooling. The building that had been redesigned to stop injuring pedestrians would now consume substantially more energy for the entire duration of its operating life than its original design had intended. The cost of the failure did not end with the renovation invoice. It was encoded into every utility bill going forward. The glass was not the only structural concern that had accumulated by this point. Occupants on the upper floors had been reporting something that was difficult to quantify but impossible to ignore. In high winds, the building moved. Not by structural engineering standards. The movement was within parameters that engineers described as technically acceptable. But it was perceptible, disorienting enough that some workers reported motion sickness. Uncomfortable enough that it became a documented occupancy issue. Engineers constructed a detailed scale model of the tower and the surrounding Back Bay environment and tested it in MIT's Wright Brothers wind tunnel. The results confirmed that the building's dynamic response to wind loading was more severe than original design projections had anticipated. The solution was a tuned mass damper, a technology still relatively uncommon in American skyscrapers at the time. Two enormous steel boxes were fabricated and installed on the 58th floor, each approximately 17 feet square and 3 feet high, each filled with lead and weighing approximately 300 tons. Combined, the system totaled roughly 600 tons of counterweight. The boxes sat on lubricated steel plates and were connected to the building's structural frame through springs and shock absorbers. When wind pushed the tower in one direction, the mass lagged slightly behind the building's movement, and that lag created a counterforce that dampened the oscillation. The system cost approximately $3 million, but the wind tunnel study had revealed something that made the motion sickness problem look secondary. Analysis of the tower's lateral load resisting system under specific wind scenarios, particularly gusts loading the building's narrow faces, showed that the original structural design carried insufficient margin. Under certain conditions, the calculations indicated that the tower could be at risk of failure. Not uncomfortable, not costly to repair afterward. Failure. Think carefully about what that finding represents. This was not a theoretical concern about a building still on the drawing board. This was a completed 60-story tower with people working inside it, located in one of the most densely occupied neighborhoods in a major American city, and the engineers who had studied its wind response most closely were not prepared to state, with confidence, that it could survive every storm Boston's coastal climate might produce. The response was substantial and conducted almost entirely outside public view. Approximately 500 tons of diagonal steel bracing were added to the building's interior, along with roughly 300 L-shaped steel reinforcement beams. The reported cost was approximately $5 million. This was not a comfort upgrade or a long-term maintenance improvement. It was emergency structural reinforcement of an occupied building, performed because the original engineering had left a margin that independent analysis found inadequate. A life insurance company had constructed a headquarters that, for a period of its existence as a completed and occupied structure, carried genuine uncertainty about whether it could remain standing in a severe storm. There is no way to improve on that sentence. It stands exactly as it is. In 1975, John Hancock filed suit against IM. Pay and Partners and 5 other firms connected to the design and manufacture of the original glass panels, seeking to recover the costs of replacing all 10,344 units. The case was settled out of court in 1981. The terms were not disclosed. The non-disclosure agreements that had already enclosed the engineering investigation extended into the legal resolution, ensuring that the full technical and financial account of the failure remained sealed. Trinity Church had its own litigation track running separately, covering excavation damage, falling glass, and a range of other claims, generating years of additional legal proceedings on a parallel timeline. The combined effect was a project that had failed structurally, financially, and reputationally, and had then managed, through sustained legal strategy, to suppress most of the detailed technical record of why. Records that did emerge through the Trinity litigation revealed one additional detail that has a particular quality to it. The building, even after the reglazing was complete, employed spotters. Personnel stationed with binoculars and polarized lenses, scanning the glass skin of the tower from ground level, looking for panels that had begun to darken, a visual indicator of internal stress. When flagged panels were identified, they were scheduled for replacement before failure. A premium office tower in one of Boston's most historic neighborhoods required continuous human surveillance of its own exterior walls to prevent them from injuring the people walking beneath them. The building employed lifeguards. The John Hancock Tower opened for occupancy on September 29, 1976, approximately 5 years behind its original projected schedule, at more than double its original projected cost. After damaging a National Historic landmark, raining glass panels onto public streets, spending years partially covered in plywood, and requiring 600 tons of counterweight and 500 tons of emergency steel to reach a condition its engineers considered safe. In 1977, the American Institute of Architects gave it a National Honor Award. The architecture profession saw clean proportions, a rigorous geometric concept, and a compelling relationship between a modern tower and its historic surroundings. The public had spent several years watching the building damage a church, close their streets, lose its own skin, and require emergency structural surgery to remain standing. Both of those things were simultaneously and completely true, which is the specific kind of institutional irony this story has been building toward from the beginning. The building stands today at 200 Clarendon Street, renamed after Boston Properties acquired it. The tuned mass damper operates on the 58th floor, 600 tons of lead counterweight silently absorbing every gust that presses against the glass. The tempered replacement panels have held for decades. The diagonal bracing added in the emergency reinforcement phase remains bolted inside the frame, invisible to everyone who works in the building or visits it. From the outside, the tower looks exactly the way Henry Cobb intended it to look. A clean blue mirror, reflecting Trinity Church and the brownstones of Back Bay, serene and seamless against the Boston sky. The serenity is a surface. Underneath it is a foundation that destabilized its neighborhood before the building was out of the ground. A facade system that was slowly destroying itself from the moment it was installed. A structural design that required emergency correction after occupancy had begun. A legal resolution that sealed the full account of the failure. And a professional honor awarded in the middle of it. Engineering schools still teach the Hancock Tower as a case study in what happens when novel materials, aggressive formal ambition, and difficult site conditions converge without adequate testing or margin. The building designed to reflect its neighbor nearly destroyed it. The facade designed to disappear into the sky fell onto the street instead. And the company whose entire business model depended on accurately pricing risk produced as its own flagship headquarters, the most consequential unmanaged risk in the history of Boston's built environment. It is still the tallest building in New England. It is also still a reminder that in the gap between what a building is designed to be and what it actually becomes, the distance is sometimes nothing more than a few millimeters of rigid solder, installed with complete confidence on exactly the wrong side of the glass.